Welcome to the debate. Today, we're diving into what is arguably one of the most critical operational hurdles facing these massive large language models, memory and parameter management, specifically within sparsely-activated mixture-of-experts, or SMEs. Now, SMEs are, well, brilliant for their efficient pre-training and surprisingly low inference latency. But their sheer size, we're talking hundreds of billions of parameters sometimes, makes widespread deployment pretty difficult because of that huge memory overhead.
Yeah, that high parameter count absolutely necessitates compression. And I think the fundamental question for, researchers and engineers right now is really how we compress these models effectively without just degrading the incredible specialized capabilities that the experts have learned.
Pruning, which basically removes entire experts based on some kind of saliency score, and expert merging, which tries to combine the weights of two or more experts into a single functional replacement. So our central question today is, which approach, pruning or merging, is fundamentally more robust for maintaining that high-quality performance, especially, and this is key, on complex autoregressive generative tasks?
Okay, and I'll be maintaining that expert merging, despite, yes, its current empirical struggles on some tasks, isn't intrinsically doomed by, let's say, architectural flaws. I think the challenges it faces are more contingent upon current, maybe suboptimal implementation and calibration methods.
And I'll be asserting pretty much the opposite, that expert prunings, especially when it's guided by these novel criteria like REAP, is demonstrably superior, precisely because merging introduces an unavoidable, an irreducible theoretical error that's rooted quite deeply in the SMO architecture itself.
All right, so my argument for pruning really begins with the mathematics. When you look closely at the SMoE layer, the router's job, its core function, is to apply independent, input-dependent control to each expert. It dynamically chooses, who gets the steering wheel for any given token. Expert merging, just by definition, sacrifices this independence. You're essentially tying two expert functions together and forcing the router to treat them as a single, static combination. And this constraint results in what the research terms a functional subspace collapse. A functional subspace collapse. Can you elaborate just a bit for the listener what that means in, let's say, practical terms?
Certainly. Imagine the full SMoE model has learned this vast landscape of specialized functions. Think sharp peaks and deep valleys representing unique, highly differentiated tasks. The collapse means the model kind of loses access to those high-resolution, unique functions. It pulls everything towards a more generic, averaged center point. Pruning, conversely, maintains that independent router control over the remaining experts. It preserves the geometry, the shape of the functional manifold. We're essentially just removing some dimensions, not collapsing the existing ones onto each other. And our approach, router-weighted expert activation pruning, or REAP, succeeds because its saliency score is, well, quite clever. It doesn't just look at how often an expert is used, but critically also how much computational energy, or functional magnitude, that expert actually contributes to the final output. This allows us to achieve, superior near-lossless compression, even at 50% reduction, on really demanding tasks like code generation. So, look, I see why you think combining experts sounds efficient on the surface, but let me give you a different perspective. Merging is fundamentally flawed because it ties those dynamic gates, leading straight to an unavoidable mathematical approximation error.
Okay, that's a compelling claim about the gates being tied. However, while I certainly acknowledge the sharp empirical underperformance of merging on these generative tasks, the data is clear there. We have to remember that merging has shown superiority on simpler tasks, specifically things like discriminative benchmarks, multiple choice question answering, for example. That suggests the error isn't quite universal. It seems contextual. Now, let's talk about that theoretical, irreducible error you cite. If you look at the math, that error is actually dependent on two critical factors. One is the policy variability, basically how often the router switches between the two experts being considered for merging, and the other is the expert gap, which is simply how functionally dissimilar those two experts are.
Right, the distance between their learned weights, essentially.
Exactly. So if the experts chosen for merging are already highly similar functionally, that expert gap term basically vanishes or gets very small, and the error dramatically decreases. The difficulty we've seen documented in merging algorithms seems to stem from these deeply practical, almost engineering challenges. Things like the non-local nature of merging experts across distributed systems, the high cardinality of potential expert clusters, and the often poor singular vector alignment between clustered experts, even after trying permutations. These feel like implementation hurdles related to how we choose to merge, not necessarily a fundamental theoretical barrier preventing the concept itself. So, yes, that's a compelling argument regarding the policy variability. But have you considered the possibility that the current merging algorithms we have, like MSMoE and HCSMoE, are simply failing to coherently combine experts that are maybe too diverse rather than the whole concept of combining them being intrinsically doomed from the start?
Okay, let's delve deeper into the nature of that error then, because that brings us right to our first contention, the irreducibility, as I see it, of the merging error. When we look at the mechanism, pruning fundamentally seeks to minimize an error that's proportional only to the low average utilization of the expert being pruned. It remains entirely insensitive to the router's learned policy variability. It just doesn't care if the router was dynamically switching between experts 1 and 2, wildly based on the input. It simply removes expert 2 if on average it wasn't used much.
And that's why pruning the low-usage experts is generally effective, right?
Precisely. Merging, however, is trying to approximate a dynamic mixing function where the router is actively choosing expert A or expert B based on the specific input with a single static constant convex combination. This static approximation inevitably introduces an error term that is mathematically proven to be proportional to the variance of the router's policy. So if the router has learned a complex, input-dependent switching behavior between those two experts it needs to merge, the merge operation is catastrophically penalized because it forces a static average where a dynamic decision was actually learned and needed. This dynamic-to-static approximation error is what I argue makes the error unavoidable if we want to compress specialized functionality effectively.
I'm sorry, but I just don't quite buy that the error is truly insurmountable in all cases. You seem to be focusing on a theoretical worst-case scenario where the merging algorithm happens to select two highly distinct experts that also have highly variable routing policies between them. But doesn't this just point to a flaw in the selection process itself? If the policy variability is high, it implies the router views those experts as functionally distinct for some inputs and maybe similar for others. If we could significantly improve the clustering methods to genuinely isolate truly redundant experts, those where both the policy variability and the expert gap are minimal, then that static approximation error you described would drastically decrease, wouldn't it? We also have to look at the practical convergence of these methods. Empirical data shows that even sophisticated merging techniques, like HCSMoE, often end up generating a really high proportion of what they call singleton clusters.
Right, those are experts that the algorithm itself deems too specialized to merge with anything else.
Exactly. They are effectively being protected, or you could almost say pruned, by the merging algorithm, because the clustering process recognizes their functional uniqueness. This suggests that even these merging algorithms are functionally mimicking pruning for the most highly specialized parts of the model, while maybe struggling with the effective compression of the remainder. If we could just improve the clustering to identify and merge only the truly redundant, functionally overlapping experts, then the theoretical hurdle you're describing shrinks considerably, it seems to me.
Well, I appreciate that focus on optimizing the engineering side, but I think the failure mechanism we see is robustly validated by the results, which brings us directly to our second point of contention, the stark empirical evidence when comparing generative versus discriminative tasks. If the error were merely some localized issue of poor clustering choices, I don't think we'd see such a consistent and severe drop-off specifically in generative quality.
Okay, let's discuss that failure mechanism then.
The theoretical fault line I mentioned between the dynamic routing and the static approximation seems robustly validated here. merging performance just drops severely. I mean, often catastrophically. We're seeing drops of 40–50% in accuracy metrics at 50% compression on complex generative tasks. Things like coding benchmarks, specialized math problems, creative writing. REAP, meanwhile, maintains accuracy remarkably well. And this discrepancy is key. Discriminative tasks like multiple choice questions or just simple perplexity calculation often only require a simplified function to succeed. They don't really test the model's ability to maintain high-fidelity output over hundreds of autoregressive steps. So the average expert resulting from a merge often suffices, and that masks the underlying functional collapse.
That's an interesting point, though I might frame it a bit differently. I completely agree that REAP's empirical success is, well, undeniable, but I'd argue that success is inextricably linked to its specific saliency criterion. REAP seems to accurately quantify an expert's importance by looking at its direct contribution to the overall output magnitude, the energy it imparts. Current merging baselines, however, they tend to rely on clustering based on simpler metrics, like just usage frequency or the cosine distance of some representative weight vectors.
Metrics that are essentially blind to the actual functional contribution, yeah?
Exactly. And these metrics might simply fail to adequately capture the necessary functional magnitude that's required for the kind of high-quality, complex generative outputs we expect from a state-of-the-art LLM. So the generative failure of merging might simply be attributed to the lack of a saliency-aware clustering approach that's equivalent to ARP, rather than some intrinsic impossibility of combining parameters effectively. What if we clustered based on functional significance and functional overlap instead of merely vector proximity? Perhaps merging could avoid the catastrophic functional collapse you observe in those cases.
I'm still not convinced by that line of reasoning, because the functional subspace collapse seems to be a direct geometric consequence of tying the gates together, which is fundamentally independent of the clustering metric used to select which experts get merged. And this leads us to contention 3, the actual geometric alteration of the functional manifold. When we visualize the function space using techniques like PCA, the differences are really quite striking. Pruning clearly preserves the functional geometry. The surviving experts, they maintain their original specialized positions. They simply occupy a reduced coordinate subspace of the original manifold.
Meaning the experts that remain are still functioning largely as the specialists they were trained to be.
Precisely. They retain their functional identity. Merging, however, causes this visible contraction. The visualizations clearly show the functional space contracting dramatically inward toward the manifold center. And this contraction is most pronounced in the late, highly specialized layers of the model, where you'd expect functional diversity to be highest. This geometric alteration is effectively the physical visualization of that loss of independent control I mentioned earlier. The router, because it's forced to apply a summed gate value to a static combination of functions, can no longer independently modulate those underlying functions, resulting in that severe functional collapse we discussed. You can see, in some cases, up to 100-fold reduction in the spread of the learned functions in these high-granularity architectures after merging.
Okay, I acknowledge the severity of that visualization, and that contraction is certainly, well, alarming. However, couldn't this visual collapse, particularly its severity in high-granularity models, strongly suggest that the merging algorithms are simply attempting to combine experts that are just too functionally distinct in the first place? When you actually look at the raw data, the L2 distance between the experts being clustered by these methods often greatly exceeds the distances observed between experts in, say, optimized, fine-tuned checkpoints. To me, this looks like evidence of poor partnership selection by the algorithm. If the experts genuinely had significant functional overlap, then the static approximation error should be minimal, and the geometric contraction would likely be much less severe. So the core constraint maybe isn't the theory of combining them per se, but the practical difficulty in finding and then coherently combining experts that genuinely share significant functional overlap. A challenge that the existing clustering metrics used by baselines like MSMoE and HCSMoE clearly seem to fail at respecting.
But if the goal of compression is aggressive reduction, let's say 50% like in the studies, you often must merge experts that are functionally distinct simply to hit that target number of experts remaining. If the architectural constraint, the tied gate, prevents a high-fidelity approximation when those experts are distinct, and the router policy between them is complex,
then it seems merging is intrinsically limited in its capacity for high-ratio, high-fidelity compression, regardless of how perfect your clustering algorithm might eventually become.
That is a fair articulation of the potential trade-off, I'll grant you that. It forces us perhaps to acknowledge that merging might simply not be the right tool for the most aggressive compression ratios if absolute maximum functional fidelity must be maintained above all else. However, the theoretical possibility of effectively merging functionally overlapping experts, perhaps at lower compression ratios or with smarter selection, still remains, I think, a worthwhile research goal. It could potentially yield a solution that preserves both parameter efficiency and architectural specialization in a way that outright removal might not.
So I think this discussion has really underscored a vital lesson for LLM deployment. While compression is absolutely necessary for scale, the choice of methodology must be driven by the required downstream task quality. Merging demonstrates, let's say, reasonable utility on metrics that only require a simplified function, maybe some discriminative tasks. But for robust, high-quality autoregressive generative capabilities, which are really the tasks these modern LLMs are truly built for, the theoretical irreducible error caused by policy variability, combined with the empirical functional subspace collapse we see, seems to make current merging techniques fundamentally suboptimal. The success of pruning methods like REAP clearly demonstrates the critical importance of preserving that independent, dynamic coordination between the router and the individual experts.
Yes, we certainly agree on the empirical reality today. Pruning, particularly when employing a sophisticated saliency criterion like REAP, shows a clear and consistent advantage on these complex generative tasks. That much is evident. However, I think the core of our debate confirms that merging's challenges extend beyond a simple theoretical brick wall. The current failings appear heavily tied to the engineering difficulties, things like non-local expert merging, navigating high cluster cardinality effectively, and critically, finding clustering strategies that can accurately measure and respect the functional gap between potential merge partners. So there remains, I believe, a compelling, though admittedly difficult, avenue for future research to develop new merging algorithms that can successfully mitigate that policy variability issue without completely sacrificing the architectural specialization that SMoEs offer.
And I think the material conclusively demonstrates the absolute necessity of comprehensive downstream generative evaluations, stressing that discriminative metrics alone are wholly insufficient proxies for judging actual, useful LLM quality.
All right, welcome. Today we've got a really cool detective story from the world of AI. We're going to uncover this hidden flaw in the way we've been trying to shrink these giant AI models. And then we'll look at a breakthrough that shows us how to intelligently, and yeah, you'll see why I'm using this word, reap their power right on your own machine. So, you know these huge models, right? Mixtral, DeepSeek, Kimi-K2, the absolute titans of the AI world? Well, they all share a secret. And it's not just that they're incredibly powerful. Nope. It's something hidden deep inside their architecture, the very thing that makes them so dang efficient. And here it is, the big secret. They're not one giant single brain trying to do everything at once. No way. Think of them more like a company, right? They're built with these teams of specialized experts, and each one is an absolute master of its own specific job. Now, that structure is brilliant for sure, but it creates this huge memory problem. So the question we have to ask is, if you're the boss and you need to downsize this company, how do you do it? I mean, how do you make the team smaller without firing your star performers and losing the exact talent that makes your company or your model so special in the first place? Okay, so let's get into the big problem here. Power versus size. It's pretty simple, really. The best AI models are almost always the biggest ones. They have just a massive number of parameters. You can think of those like the connections in a brain. And yeah, more parameters usually means more power. But it also means they need a colossal amount of memory to actually run. So the fancy name for this architecture is a Sparsely-activated Mixture-of-Experts, or SMoE for short. But honestly, just stick with that team of specialists idea because it's perfect. You've got this manager, it's called the router, and when a job comes in, let's say, write me a Python script. The router doesn't bother the whole team. Nope. It knows exactly who to talk to and sends the job straight to the coding expert. Then the next task is write me a sonnet. Boom, off to the poetry expert. See? Only a tiny, specialized part of the model gets activated for any one job. It's incredibly efficient. But, and there's always a but, right? Here's the catch. To have all those specialists just waiting on call, the total number of parameters, the total size of the company just skyrockets. We're talking about models like Kimi-K2 that have over 1 trillion parameters. I mean, that is just massive. It's way, way too big to run on your phone or your laptop. And that creates a huge bottleneck for pretty much everyone. So how do we fix this? How do we shrink these things? Well, 2 main strategies popped up: pruning and merging. And for a little while, one of them seemed like the totally obvious common sense choice. But as this new research shows, well, let's just say common sense was dead wrong. Okay, so here are your 2 options. Option 1, pruning. This is like laying off your least effective employees. The team gets smaller, sure, but your top performers are still there, doing their thing. Option 2, merging. This is more like forcing your poet and your programmer to share an office and become one single generic creative consultant. And for a while, a lot of people thought merging was the way to go, especially because it seemed to work okay on really simple, like, multiple choice tests. Okay, to really get why merging is a problem, let's use a new visual. Imagine all the model's different skills as a vibrant constellation of stars. Each star is one of those experts, a unique talent. And they're all spread out. A bright, diverse, spread-out constellation means you have a really powerful and versatile model. But here's the twist. This is what the researchers found. When you merge those experts, you don't just get a smaller constellation with fewer stars. No, you get something they call functional subspace collapse. The entire constellation just collapses in on itself. It loses all its diversity, all its structure. All those unique skills get averaged out into one single generic and, frankly, much dimmer point of light. And this is the smoking gun right here. The paper proves that merging creates what's called an irreducible error. And why does that happen? Because the manager, that router we talked about, it loses its ability to pick the right specialist for the job anymore. When you average all the experts together, you completely break the one thing that makes the whole system smart in the first place: its ability to make these sharp, independent choices for each task. So, okay, if merging is this flawed strategy that basically just cripples the model's creativity, what's the alternative? Well, we go back to the underdog of the story: pruning. Firing experts, not smushing them together. Let's go back to our constellation. With pruning, yeah, some of the stars just vanish. But, and this is the important part, the ones that are left stay exactly where they were. The overall shape, the diversity, the structure of the team's talent, it's all preserved. The router can still look at this smaller team and pick the perfect expert for the job, because they're still specialists. Okay, but this brings up the next obvious and very important question. If you're going to fire half your team, you better have a really smart way to decide who gets the pink slip and who gets to stay. Because just firing the person who seems the least busy, well, that's not good enough. Turns out that can lead to catastrophic failure. To do this intelligently, you need something called a saliency criterion. It's a fancy term, but just think of it as a performance review for your AI experts. It's a scoring system that measures just how critical each expert is to the final product. A high score means you're valuable. A low score? Well, you're on the chopping block. And this is where the new paper comes in with its big breakthrough. It's a brand new method for running that performance review. It's called REAP, and it is a much smarter way to figure out who to prune. Okay, so REAP stands for Router-Weighted Expert Activation Pruning. Here's how it works, in 3 pretty simple steps. First, it looks at how often the manager, the router, actually picks an expert. Pretty straightforward, and this is the absolute key, it doesn't stop there. Second, it measures the impact of that expert's work. How much did their contribution actually change the final answer for the better? See, an expert could be chosen all the time, but contribute almost nothing useful. Finally, it just combines those 2 scores and prunes the expert who contributes the least overall. I love this part. It's not just about being busy, it's about making a real difference. Now, that all sounds great in theory, doesn't it? But does it actually work in practice? Let's look at the proof, the hard numbers. And trust me, the results are pretty staggering. Okay, get this. They took the Qwen3-Coder model, which is a specialist in writing code. They used REAP to get rid of a full half of its experts, 50%. And it still retained over 97.5% of its original coding performance. Think about that. It's half the size, but it's pretty much just as smart. That is basically lossless compression. And this chart shows you exactly where merging just completely falls apart. Look at the coding task. These are generative tasks that need creativity, they need precision, and the merging methods just collapse. Performance plummets. But REAP, still incredibly strong. Merging is fine for, simple multiple choice stuff, but it totally fails the real-world test of actually creating something new. And listen, REAP doesn't just beat merging. It crushes other, simpler pruning methods, too. Just look at frequency pruning here. That's the simple method of just firing the least used expert. At 50% compression, the coding score drops from 0.66 down to almost 0. It completely breaks the model. And meanwhile, REAP is right up there at the top, barely even a scratch on the original performance. That smart performance review, it really, really pays off. So, why should you care about all this technical stuff? Well, it matters a lot. It means we are closer than ever before to running these incredibly powerful specialized AI models right on our own laptops. It means researchers who don't have access to giant, expensive server farms can actually work with these state-of-the-art models. It lowers the cost, it lowers the energy needed to run AI, and it just paves the way for a whole new generation of super efficient custom AI tools built for exactly what you need. And it all leads to this one final, really exciting thought. For years, right, the biggest AI brains have been locked away in these massive data centers. But with breakthroughs like this, we are finally learning how to shrink the brain without losing the smarts. So the question isn't if we can do it anymore. The real question is, what are we all going to build when a trillion parameter mind can finally fit in your pocket?